exercise about integrals and okay. It is charging the blackboard. You should see in a couple of minutes what is on my desktop. Okay. So we had very little about some exercise about matrix operation and eigenvectors computation. So maybe we can begin from this one, and I will give you some hints. Okay. I'll take the pen. Right. So let's take some example with from your exams, and we can discuss a linear system of first order differential equations. As you know, differential equations are equations where both the function and the derivative of the function are in the equation. So you need to find an equation, a function that satisfies more conditions, of course. And in order to solve these kind of equations, you have to work with matrices. Okay, so linear differential equations are of this kind. This is the derivative with respect to t, to the variable t, and normally t is seen as the time, and a times x. I think you use this underline in order to describe a vector. Okay, it depends in which dimension we are, but normally you solve linear systems where there are two equations. So that means that the vector x dot corresponds to a pair of coordinates that are x1 and x2. So you can see x1 and x2 dot, and this is a column vector 2 by 1 by 1, and this is equal some matrix A that is 2 by 2, multiplied. This is the multiplication, the product row by column. That means that if you have, for instance, let's see, let's give a matrix from the example. We have 1, 6. I don't know if you solve some exam papers, but this comes from an exam, and this is the case without the column vector b, but we can add the column vector b, and we have to solve first of all the equation without the known term. That means this equation. Okay, to remark, the product between two matrices means that the solution, so the result, will be, first of all, it is 2 by 2 multiplied by 2 by 1. Okay, if you know that the matrices can be multiplied, and this is the case because the number of the rows of the first matrix are equal to the numbers of the column, the numbers of the column of the first matrix are equal to the numbers of the row of the second matrix. This should be equal, and the result will be a new matrix where the number of the row is this first number, and the number of the column will be 1. So the result will be a new matrix that is 2 by 1. Okay, every time you have two matrices, you should remember that you have the new dimension, new order of the matrix given by the number of the row of the first one times the number of the columns of the second one. Okay, so first of all, we find, I'm sorry, I didn't write the result. So this is 1/6 times x1, first entry times first entry, plus 1 times x2, second entry times second entry. This is the reason why we should be we should have the same number in the row as the same number in the column. And then we compute minus 1/3 x1 minus 1 times x2. So this is the result, and this is a matrix 2 by 1. We have only one column because this is a sum. This should be a number. Okay. Then the system is the derivative with respect to x. This is x1 dot. So the x1 over dt, and the derivative of the second one over dt. These are two components, are equal. Okay, so let's begin with the general solution of the homogeneous system. That means that we have these two functions, x1 depending on t and x2 depending on t, such that we have so we let b come out after that, after we computed the general solution of this x dot equals a times x. As you know, this solution could be seen as the solution where we have first in one dimension, because you remember that if we have only one dimension, only one value, so x dot equals alpha x, so we already knew the solution because this is in exponential form, and this is an exponential where we have some constant c times e alpha t. Okay, so that means that we have some idea that the solution will be a linear combination of this solution, or maybe something that is in the same form. Okay, and this comes from the computation of the eigenvalues of the matrix. The eigenvalues of the matrix are numbers such that eigenvalues of the matrix A are normally called lambda, and are let's say lambda I, lambda 0, lambda 1, and so on, such that the equation such that multiply the matrix such that there exist eigenvectors, let's say V, such that the multiplication by the matrix A is the same as the multiplication by a scalar lambda. Okay, these are normally real values or maybe complex values, but these are in some field where we pick up values, so normally real numbers. Okay, so what is what does it mean if we take the whole equation and we rewrite on the left side of the equation everything, and we remember that of course we are dealing with square matrices, A is square, and if we multiply by the identity, in this case we can choose some order n by our exercise will be I2. This is in our case 1001, and this is the identity matrix. This is the matrix that multiplied by anything gives the same number. A vector multiplied by identity matrix remains the same vector, and so every matrix. That means that if we multiply, in this case we have two dimensions times lambda times v, we can take out the value of this vector v. This is the eigenvector vector. Okay, and this should be 0. That means this whole matrix 2 by 2 multiplied by the vector should be 0. That means that this is an homogeneous system where we have a matrix, a solution that multiplied by the vector gives 0. What does it mean? It means that since the eigenvector cannot be 0, we have to find when the matrix has not unique solution, because the unique solution would be 0. Okay, and we know that if we solve a linear system, there is unique solution if and only if the rank of the matrix is the maximal rank, so it should be 2. In this case, we have a so we should state that the rank of A is different from 0. And if we have some matrix, some square matrix, and we know that the rank is maximal, so the same order, this holds if and only if the determinant of the matrix is different from 0. Determinant of A is different from 0. So we have maximal rank if and only if the determinant is different from 0. That means we don't have maximal rank if the determinant is 0. Okay? And the determinant of this matrix is called the characteristic polynomial, that is called P of lambda. P of lambda, that is the determinant of this new matrix, lambda times I, this identity matrix, should be equal to 0. The solution of this equation will be this lambda, these eigenvalues that give us this equality. Okay? So, in order to find the eigenvalues, we can compute the determinant of A minus lambda I. That is, the lambda remains multiplied by these ones on the principal diagonal, and that means that A minus lambda I will be 1/6 minus lambda, 1 minus 1/3 minus 1 minus lambda. And we should compute this polynomial and compute for which value of lambda this polynomial is equal 0. So the determinant of this polynomial will be 1/6 minus lambda times minus 1 minus lambda minus 1/3 times 1 plus 1/3. Okay. So we can compute everything. Lambda square plus plus lambda minus 1/6 lambda, that is plus 5/6 lambda, and then we have minus 1 times times 1/6, this is minus 1/6, plus 2/6, it is 1/6. Okay, this should be equal to 0. Okay, you have, I think, another type of computation that you can use, but normally for matrices that are 2 by 2, because it is somehow different from bigger matrices, but you could have computed the same by giving lambda square minus the sum of the values on the diagonal times lambda plus the determinant of lambda. If we compute, we obtain lambda square minus the trace, this is the trace of A, trace is equal A11 plus A22, and in this case is 1/6 plus minus 1, 1/6 plus minus 1, so let's use minus 1 directly. Okay, minus 1 times lambda plus the determinant of A, and the determinant of A is minus 1/6 plus 1/3, so it is 1/6. Okay, so this is the determinant of A minus lambda I. But this is a formula that it is maybe this quick here. Minus 5/6 is plus 5/6 lambda plus 1/6 plus 1/6. Okay, so as you can see, it is the very same. Okay, so which are the values of lambda that solve this equation equals to 0. Okay, the values of lambda are two numbers that multiplied gives 1/6 and added gives 5/6, and this number minus 5/6. This number are minus 1/2 and minus 1/3. So minus 1/2 and minus 1/3. You can use different way in order to compute this one. You can use the quadratic formula. So minus b plus or minus square root of delta divided by 2a. But anyway, you have found two values. This is good because you can compute the eigenvectors that are associated to these eigenvalues. So let's change board. I think everything is clear because I know that you already seen this kind of competition in your lectures, but if you have some questions. Yes? Yes.
Shouldn't the sum be plus 5/6?
Sorry?
The sum should be 5/6, right?
Okay, if you are factorizing a special trinomial, the sum of the two terms that you have in the parentheses should have plus 5/6 as sum. Let's say lambda minus a lambda minus b, okay? And you have lambda plus 1/2 if you want to decompose this trinomial. Lambda plus 1/2 times lambda plus 1/3. These are the two numbers for which the product is 1/6 and the sum is 5/6. But these are not the roots of the polynomial. These are the opposite.
Okay, I understood.
Okay, because if you want to factorize the trinomial, you write this with the same sign, because everything that normally change is the sign of this term that should be the sum, because the product, if the two roots are on the same sign, the product is always plus. If the roots are discord, that means one is positive and the other negative, to change these two signs will be the very same, because the product will have plus by minus or minus by minus or minus by plus. This is the same. Plus in front of this number means that we have minus the sum of the two roots. If you know the formula, if you've seen the formula at school, you've seen this formula, and you know that the polynomial, if you compute x1 and x2 as the roots, the sum is the opposite of this one. In our case, we don't need to divide by a because we already have 1. But the solutions will be the same, because if we multiplied the whole trinomial by 6, we obtain the same solutions. And the product of the two roots is always the known term divided by a. If you remember this one, you know that if you want the roots, you have to change sign. If you want only to factorize, you can take the two elements that are added together. Okay, I think now it is clear. So, so we were by the different eigenvalues. Let's take the first one and name minus 1/2. So, if the first one is minus 1/2, we can compute the eigenvector. That means this vector v that satisfies the equation a times v equals lambda times v. In this case, lambda 1. What was lambda 1? Lambda 1 was minus 1/2. So we have to solve the homogeneous system, where we substitute to lambda, so it is minus 1/6 plus lambda 1 is minus 1/6, then minus 1/2. Okay, and then we had the 1 and 1/3 in this place, and instead of 1 we have 1. No, I'm sorry, I wrote so we had the plus 1/6 minus 1/2. I'm not sure if you used a minus lambda I or lambda I minus a. We can continue in this with this method, but it is the very same, because I wrote in the previous board AV minus lambda V, that gives us A minus identity matrix times lambda. But if I have taken on the right, everything on the right side, that will be the same, 0. Okay, and this will give you lambda times the identity minus a times v equals 0, and this one should be determinant equals to 0. But we know that a polynomial and its opposite have the same roots, so it's the very same to compute this one or the other one. Okay, so you can maybe do this computation with me, and then try to compute the same by changing the sign, but it is the very same. Okay, so this should be equals to 0, and 0 is not a value, but it is a vector, the vector 0, that has the same dimension of the matrix that is the result of the product of the left hand side, 0, 0. Okay, so we are looking for the eigenvectors that are associated to this solution lambda 1 equals minus 1/2. We solve this equation and we find the values for x1 and x2. So 1/6 minus 1/2, it is 1/6 minus 3/6 is minus 2/6, so minus 3/6. 1 minus 3 is minus 2. Minus 2/6, so it's equal minus 1/3. I think. No, I'm sorry. It is minus lambda. This is a plus. This is minus lambda. So it is 1/6 plus 1/2. It is 1/6 plus 3/6 is 4/6. It is 2/3 plus 2/3. Okay. So one has only to remember which is the first one and what we are subtracting. So it is 1 plus 3, it is 4/6, and this is plus 2/3. So and this one, it is minus 1 plus 1/2, it is minus 1/2. So the two equations are 2/3 x1 plus 1 times x2 equals 0, and minus 1/3 x1 minus 1/2 x2 equals 0. Okay, so we can compute from instance from the first equation, we can compute x2 by putting everything else on the right hand side, minus 2/3 x1. Okay, and from the second one should come the same, because we already know that if we have maximal rank, there are two values, but if we have rank different from 2, we only have the number of the unknowns, so that is 2 minus the rank of A, 1, so we have 1 degree of freedom. So if you compute the same of the second one, you will have the same computation. Okay, so if we put x1 equals to t, we can write the eigenvector as eigenvector as t and minus 2/3 times t. And if we put outside the multiplication by the value t, where t belongs to the real numbers and is different from 0 because the eigenvector shouldn't be 0, it is t times, and we have 1, and we have a minus 2/3. Now we have a vector space. This is all the multiples of this vector, and the vector is 1 minus 2/3. The same computation is easy to do by the second one, lambda 2. This was minus 1/3. Then we have the matrix with 1/6 minus 1/3, that is 1/6 plus 1/3. 1. This everything remains the same. Then we have minus 1 plus 1/3. This is the matrix A that we should we should multiply by x1 and x2, and then that should be equals to 0, of course. Then we have two equations. So 1/6 plus 1/3, it is as 1/6 plus 2/6. So this is 3/6, it is 1/2. 1/2 x1 plus 1 times x2 equals to 0. And the second one, you really don't need to compute this one, but okay, I will write it. Minus 1/3 times x1. And then we have minus 1, so minus 2/3 x2 equals 0. And then we can compute, for instance, from the first one, the value of x2. And by putting everything else on the other side, it is equal minus 1/2 x1. With the same methods, we found let's say key, and the eigenvector will be let's write key minus 1/2 k, and this is equal k times 1 minus 1/2. Okay, so I think this should be very clear. Okay, so what is the general solutions that we can write as for the homogeneous problem that we had in the previous slide? Okay, this one without b. The general solution is of this type with the exponential function, and since we do something like an integration, we do have constants that we don't know, but no problem. We have the two eigenvectors. Of course, we can multiply this one for everything we want. That means if I don't want fractions, I can multiply everything by 3. This is a multiple of the eigenvectors, and it is a vector that multiplied by a will be lambda times the vector itself. Anyway, we can multiply and take 3 and minus 2, and this remains the very same. So the eigenvector is this one, okay? This is the eigenvector. This is a vector that we need in order to write the solution of the differential equation. Okay, so what is the general solution of this homogeneous problem? We have x1, x2 equals vector some constant c1 times the first eigenvector, and this is 3 minus 2, times e multiplied by t by someone have yes, okay, yes, I've seen the message. I told Professor last week that we didn't have the possibility to do the exercise last week, and then I booked the exercises last week, but I thought you've seen in the scheduled, but there's no problem. A question: did I upload the old slides, or are some slide missing? Because normally I do upload the slides in this chat. The only problem that I had was in Virtuale, but maybe I will manage to add these slides in Virtuale. Maybe.
I remember
Yes.
some slides uploaded to Virtuale, and I was just asking if you could upload also the lessons of today, the
Yes.
exercise.
Yes.
Yeah. Okay.
Yes.
Thank you.
Yes. Of course. Of course. Now, my question was maybe I forgot to upload some old slides, but if you can check, maybe then you ask me for the old slides. I think I've uploaded everything, but this of course these slides I
Okay.
will upload. Okay. Um, okay. So we were by the eigenvalues of the exponent in this case, and the exponent is the lambda 1, so minus 1/2 times t. And this is a linear combination of the two solutions. If you remember what I told you, but I think you already had in your lessons, the solution is of this kind, okay? But since we are not in one dimension, we have a linear combination of two solutions of this kind, where alpha is seen as the eigenvalues lambda, okay? This is the similar explanation that gives us this kind of solution. So we have the second one that is we can multiply by 2. We don't need to have fractions, so we multiply by 2. 2 times 1 minus 1/2. It is the very same, okay, but maybe it is faster to compute. It is 2 and minus 1, okay? Because every eigenvector is a multiple of an eigenvector that solves the same equation. 2 minus 1, so we don't have fractional coefficients, e multiplied by minus 1/3 t. Okay, what is this? This is the general solution that depends of two constants, because we didn't have any initial condition that were given to us, and both eigenvalues, as you've seen in differential equation that we solved last time, since the eigenvalues are negative, when the time, normally is the time that grows to plus infinity, the system is, the solution is stable. And the question is, if we add b, can we find the general solution in order to compute the constants and to give a particular solution? The answer, of course, is yes, and we should begin by taking the solutions of this one and adding the solution of the constant solution, where the derivative of x with respect to t is 0. Let's change the board. Okay, so since we've noticed that the solution is a steady state solution. Someone is writing. Yes, so I had a couple of exercises to solve. We can add the exercise if we have time, and if not, maybe I can send you the solution. Can you upload a picture or an image of
Yeah, I can
exercise?
send a picture. I can send a picture.
Yes, or you can send me per email. I can watch. Okay, because
No, I can send it here. I can send it here in the chat.
yes, please. Okay. If we don't have time, then I can then upload with the slide, and you can ask if you don't understand. Okay, so okay. Okay, the following system, so that's the can check. Okay, the general solution to the system initial conditions such that the corresponding particular solution converges to the steady state as T. Okay, we have 0, 0. That is yes, it is the same kind of computation that we are solving in this case. Okay, we can compute the eigenvalues because we can check and we can compute the general solution. Okay, it is the same kind, and I will try to do everything. Okay, so we were left by the computation of the general solution. Okay, so if we eigenvalues computation is always the same. Okay, so as I computed in before, these are the same. Okay, and we have the matrix that is 1, 6, -1. Okay, and we had the B that was -4 and 5. Okay. So we rewrite the system where if you think about one-dimensional cases and where the derivative of a function means the slope, you know that something that is steady is where the derivative is 0. Okay, so you have a steady state solution to the homogeneous system if you have these limits equals to 0 of fx of t. You can compute the steady state by putting x dot equals to 0. Okay, because the steady state is a constant solution. What does it mean in our more general system with the vector b that was -4 and 5? That you have, instead of x1 dot, you have 0, and instead of x2 dot, you have 0. And you have the same equations as before, 1/6 x1 plus 1 times x2 -4. And then you had minus 1/3 minus x2 plus 5. Okay, then we have a system with two variables. So for instance, we can write x2 on the left-hand side, and x2 will be equals, I'm sorry, I forgot x1. Maybe I should write it better. This is minus 1/3 x1 plus x2 and so on. And then you have, no, this is a minus. This was a -1. Okay. This was a -1, and so I can put on the left-hand side minus x2 that will be plus x2, and then it is equal minus 1/3 x1 plus 5. And then we can substitute. We can solve this system as we want, because it is a 2x2 linear system. It is very easy. I can take 4 on the left-hand side and write 1/6 x1 plus x2, but instead of x2 we rewrite the expression that we computed before. That is 1/3. This is plus x2. This is the minus. I'm sorry. I have to cancel this sign. So minus 1/3 x1 plus 5. And so we can compute x1 and x2. So 1/6 minus 1/3 is minus 1/6, because it is the 1/2. Minus 1/6, I can put minus 1/6 x1, that will be plus equals 5 minus 4. Okay, here we are, and then that means 1/6 x1 is 1, and then x1 is 6. Okay, and then what is x2? x2 is equal minus 1/3 times 6 plus 5, and then we have minus 2 plus 5, that is 3. Okay, so we have that our steady state, that is the limits of this, let's say the limits of x of t, the value, the vector for t approaching to plus infinity, because normally we think about time. It is a vector. Okay, this is the steady state. So how do we compute now the constants that solve our problem? Because we were stuck, the solution was with constants C1 and C2. Of course, what we do now is to compute a particular solution. Okay, rewrite the new solution. That means that x1 of t, remember that we had the vectors 3 minus 2 and 2 minus 1. So the vector x1 and x2 we can split in two equations, where the vector 3 minus 2 is multiplied by C1 e to the minus 1/2 t, that was the exponent given by the first eigenvalue. And so it is as an when we write the system instead of the matrix notation, but it's the very same. And then we had +2 and -1 multiplying by C2 e to minus 1/3 t, and this was -1, so C2 multiplied by e to the minus 1/3 t. And then we have the limits. When t is going to plus infinity, everything is going to 0, and what have we left is this very vector that we already computed, that is 6 and 3. Okay, so this is the general solution. Okay, and if we have initial conditions that are given in the problem, for instance, x and y, x1 and x2 of 0. Okay, let's say we have x1 of 0 is equal to, and x2 of 0 is equal 1. What we have to do is to substitute these two initial conditions in these two equations. So 2 equals 3 times C1 times e to the minus 1/2 times 0, because t is 0, okay? So that means e to the 0 is 1. So we have 3 times C1 plus 2 times C2, the same reason gives us 0 as exponent, and e to the 0 is 1, plus 6. And the second is minus 2 times C1 minus C2 plus 3. And then again, we have a linear system. We can compute, for instance, C2 by putting C2 on the other side of the equation, and it remains minus 2 C1 plus 3 minus 1 plus 2. And then we can substitute in the other one. Instead of C2, we write, so we have 2 minus 6, it is minus 4, equals 3 times C1 plus 2 times C2. So plus 2 that multiplies minus 2 C1 plus 2, and then we are done. So we have 3 C1 minus 4 C1, it is minus C1. So C1 on the left side equals 4 plus 4, 8. And then C2 equals minus 2 times 8, it is minus 16, plus 2 minus 14. And now we have computed the constants given by our particular solution for this equation. I
Sorry,
did open the other.
Question?
Yes, of course.
Yeah. What happens if the steady state is 0, 0, as in the exercise that I've sent you in the chat?
Okay, you have to substitute 0 and 0 instead of 3 and 6.
Okay, but then you have a system, the last system that you wrote, where the steady state is 0, 0, and the initial condition is also 0, 0. So what happens in that case?
That maybe you have a solution. Yes, I was trying to find out. Okay. You have a steady state. This is 0, 0, and initial condition. Now you have to find initial condition. Yes, you have to find it. This is we had initial condition. I can put the image on the slides. Okay. Okay. So you have a steady state, and you have to determine the general solution. The general solution is computed as the solution that we had with C1 and C2. And then you have to find an initial condition such that the particular solution converges to the steady state as t converges to plus infinity. So you have to compute the limits, and normally it should be something that you computed given by the eigenvalues. I can watch if if we can compute the matrix, the eigenvalues of this system, this one. Okay. Okay. So this is the system. This is an homogeneous system. We can rewrite the system as a matrix computation, as a matrix as the matrix of the system, and you have so it is x and y, but you are in two-dimensional case anyway, because you have x and y, and normally we wrote in the other exercise x1 and x2. So we can continue by writing x1 dot of t equals, and then we write the matrix, or maybe we can write the vector as a vector like before, x2 of t. Okay, and this is the matrix A. This is minus 1, minus 1/2, and 3/2, 1. Okay. Okay, and this is multiplied by x1, x2, that in this problem is given as x and y, but we have x1 of t and x2 of t. Okay, this is okay. And this has a steady state solution that should satisfy x dot equals 0. Okay, so if we compute the eigenvectors of this matrix, okay, we should use one of the two methods that I gave you, and the eigenvectors are given from this matrix. So if you compute lambda 1 and lambda 2, or I don't know, you have -1 minus lambda, or we can use the trace formula. It is easier to compute. The determinant of the matrix A, determinant of A is -1 times 1 minus -1/2 times 3/2 is plus 3/4, and then this is -4 plus 3 minus 1/4. Okay, so normally the determinant is something that gives the product of the eigenvectors, so maybe eigenvectors are one positive and one negative. So, but we compute with this formula that I wrote in the first slide, I think, second, in the first one, no, where we have lambda square minus trace of A times lambda plus determinant of lambda, and then we should find the solution of this one. So we have lambda square minus trace of A is 0. Okay. Yeah. Is someone asking something, because I hear some noises?
No, sorry, I had my microphone on.
Okay, fine. Okay, thank you. So we have the trace that is 0, -1 plus 1 is 0, so we don't have the middle term, and then we have plus determinant of A. So plus minus 1/4, that means 1/4, and this is should be equal to 0. Okay, so it is very easy because lambda square equals 1/4. We have two solutions. Lambda equals plus or minus 1/2. Okay, so then we find the eigen vectors of this one, and eigenvectors. Sorry, I wrote eigenvectors, but it was meant to be eigenvalues. This was searching for eigenvalues. Eigenvalues. Okay. Then we try to find the eigenvectors. Eigenvectors. And that means we have to solve lambda minus the first one I'm sorry, A minus lambda identity in the first one, and then we should find some vectors. If we have lambda 1 equals, let's say, 1/2, and we have the matrix A, so -1 minus 1/2, then minus 1/2, and then 3/2, and then 1 minus 1/2. And we have to solve the homogeneous system where this matrix multiplied by x1 and x2 is equal 0. x1 and x2, and that should be equal to 0. 0, 0. Okay, so, and we have minus 3/2. We can rewrite the system. Minus 3/2 x1 minus 1/2 x2 equals 0. 3/2 x1 plus 1/2 x2 is equal 0. As you can see, the second equation is exactly the opposite in sign of the first one. Namely, we need to solve only one of these equation. So let's take x2. So we have x2, 1/2 x2 equals minus 3/2 x1. Okay, I think the sign is right. So if we multiply by both sides, we obtain x2 equals minus 3x1. Okay, and the same will come from the other one. That means that this eigenvector will be, let's say, t. I'm sorry, I used t, but now I can use alpha and beta as in some example that you have. So let's say alpha is x1 and minus 3. This is a 1, not an alpha, because alpha is outside. Okay. Okay. So this is 1 and this is minus 3. Okay. And this is the first eigenvectors that corresponds to the eigenvalues 1/2. Okay. And now we compute the eigenvector, the eigenvalue corresponding to vectors in more dimension. You could find more eigenvectors that correspond to one unique eigenvalue, but for any different eigenvalue you have one eigenvector. If you have different eigenvalues, you're sure you have eigenvectors corresponding to each eigenvalue. So we have two different eigenvalues. We are in two-dimensional space, and so I'm sure we can find an eigenvector for lambda 2 that is equal minus 1/2. Okay, so we have again the matrix that is minus 1. Okay, minus 1 minus 1/2. It is plus everything plus 1/2. Not everything, only on the diagonal. Okay, don't. So we have minus 1 plus 1/2, and then we had 3/2, 1 minus 1/2, 3/2, 1 minus 1/2, and we have again minus 1/2. Okay, in order to be sure, I look 5 times. Okay, so we have to solve again a homogeneous system where the matrix A minus lambda I times x1 and x2 is 0, gives 0 as a solution. If you will have more linear algebra and in the future, we are looking for the kernel of the linear function of this matrix, but you don't need to remember that. Okay, so we have then the system minus 1/2 x1 minus 1/2 x2. In this case they are the same. You can see x1 plus 1/2 x2. They are the very. No, sorry, minus. No, I'm sorry. This is a plus. Okay, that means we have a 3. Okay. This is the right computation. I was making a mistake by putting the different sign, but this is 3/2. Okay, as you can see, they are, one of the equation is a multiple of the other equation. Okay, so then you have you have x1 and x2 that are one the opposite of the other. So, for instance, if we put x2 on the other side and we divide by 1/2, we have x2 equals minus x1. And this will be the same. x2 equals minus x1. So what do we have? We have an eigenvalues that is beta times 1 minus 1. Okay. So what is the general solution now? We have a general solution that have an eigenvalues that is negative. Okay, what was the text again? Okay. The steady state is a saddle steady state as one check from the eigenvalues of its coefficient. That is a steady state that diverge because we have the term where the coefficient of t, one of the eigenvalues, is positive. We should find the initial condition that is x of 0 equals and y of 0 equals something such that the corresponding particular solution converges to the steady state. So particular solution that we can write should be x1 of t. So the general solution, let's write the general solution, x1 and x2. And we have the first eigenvalue that was corresponding to 1/2, it was 1 minus 3. Okay. 1 minus 3. So we have C1, 1 minus 3. Okay. Times E2, again, I forgot everything, 1/2 t. Okay. 1/2 t plus C2 that multiply the other eigenvalue, that is 1 and minus 1, multiplied by E2 minus 1/2 t. I hope all computations are right, because it could be yes, I think that there are no mistakes in the computation, but if you find something, okay, and then you can ask, and then you can write me. Okay, so we have then the general solution where you have this solution that is written as in the the steady state x star y star, that is 0 0. Okay, so we have the steady state that is 0 0. Okay, that is 0 0. Okay, so what are this sad point? You have to derive and to rewrite once where one constant is 0 and the other constant is 0, because this gives a problem. That means that the only possibility that we have something that converges is to have a trajectory that has C1 to 0. To have C1 equals to 0, we have to compute C1 and C2 in order to find the initial conditions. Okay, if you look at the previous exercise that we solved, we had initial condition, and this we solved by having two constants C1 and C2 that we needed to compute. In this case, this kind of steady state will give us a solution. Let's say C1 is equal to 0, and let's substitute. Okay. Let's write in the other board. Okay, we have C1 equals 0, and we compute x1 of t and x2 of t equals C2. Of course, if it is 0, the whole term is 0. C2 times, okay, what was again? 1 minus 1, okay. 1 minus 1, and multiplied by e to minus 1 half t, and then we should have x star and y star, or x1 star and y1 star, that are our steady state, but it is 0 0. Okay, this is 0 0. That means that from this one we obtain x1 minus 0, so x1 equals C2, and the first one is 1 time e to the minus 1 half t. Okay, and x2 is equal C2 minus C2 minus C2 times e to minus 1 half t. Okay, if we have the same computation as in the previous exercise, we had +3 and +6. So it is as I wrote x1 minus x1 star, but it is 0, okay, so it doesn't count. What do we have now if we put C1 equals to 0? We have something, we have two equations, okay? Because normally if you see in the space x1 and x2 as x and y, because these are the two coordinates of points in the plane, okay? And you have c2 times e to the minus 1/2 t, that I can you have this one, that is the same as this one, okay? Means that you can rewrite x2 as minus x1. Okay, if you see it as y and x, y equals minus x. And if you put everything together, you have y plus x equals 0. What is this? In the plane. In the plane xy, it is a straight line. The bisectrix of the second and the first quadrant. I don't know if it is clear. This one. So what are the initial conditions in order to what was the question again? What is so the general solution? We have already written the general solution to the system. Find an initial condition such that the corresponding particular solution to the steady state as t going to plus infinity. What is the steady state? The steady state is 0. Okay. So what is an initial condition? Because we have to compute the limit that should gives us, as I wrote in the, I think the second slide, yes, this one, limit to t approaching to plus infinity is the steady state. Okay, for us the steady state is 0, 0. What do we have as initial condition that can give us this solution, the general solution that we have in the same form of this one, in order to let the general solution converge to the steady state. The steady state is 0, means that we should have limit for t approaching to infinity of this vector x that should be equals 0, 0. Okay, that means there is no way that this first term multiplied by the exponential t is going to be 0, because for t approaching to plus infinity, we know that the exponential, even if there is a term 1/2, is going to plus infinity. Okay, so the only possibility that we have is C1 equals 0. And what should be C2? The limit of everything that remains should be 0, 0. Or C2 times 1, E2 minus 1 half T, and minus C2 times E2 minus 1 half T, every I think we have again multiple of n imputed in the board. The C2 can be any value. Let's take an example. Let's say C1 and C2 are 0 and 3. Okay. Compute limit of t approaching to plus infinity of 3, let's say, vector wise, okay, of this one. It is not important what is C2, because we already have minus that is equal to 0, okay. Because this steady state is 0, 0. Let's say we had another steady state like the first one, 6, 3, okay, and that means what is x1 of 0 and x2 of 0 in the case of our computation. X1 of 0, I can write it there, x1 of 0 is equal C2 times 1, and x2 of 0 is equal minus C2, because it is times 1. And as you can see, there is a multiple of our eigenvector that we computed in the previous computation. So I would say you have some C2 that is that gives you the stability, because if 1 it equals to 0 and you have C2 equals to 0, you have the equation y equals minus x. I'm sure you already an idea of the of which kind of line this is. This is this straight line, okay. And if you think of the initial condition, x0 and x1 and x2 of 0, you could have any points of this straight line. What can I add? Maybe this was be an expert and the corresponding particular solution. Maybe you can take, as we computed before, a particular solution, as we computed, what was the particular solution, but we already had an homogeneous system, and by substituting the state, we did have the computation from the initial conditions. Then I think this is a question that answers itself. The initial condition could be some multiple of the first state of this. C2 can be anything. Yes, I don't think so. Without fixed point. I will send you the slides because now we've run out of time, and I think maybe somebody is
Sorry.
it is late. But I can, what if some similar rewrite, if I notice that the professor added some other equations. Yes, someone was speaking.
Yeah,
Yes.
can I ask you to solve an exercise and include it in the slides that you're gonna upload?
Okay. So I can try to add another exercise. I understand. You can send me the exercise, I add in the slide, and then I will try to solve and send you.
Okay, do you prefer me to send it by mail?
Now, if you put the file in the chat now, I can copy paste in the slide, and then I can watch it later.
Okay, thank you. I'm uploading it.
Okay. So I think all the other students are interested too, because solving more exercises is good. And I don't know if you did compute the Hamiltonian and the fixed point cases, but maybe this is the case, and I will add some comments. Okay, let me see. This is a difference equation that can be related to a differential equation. Okay.
Yeah,
Subject
because,
to specify. Yes.
I
Please.
I think that from what I have understood, that there are two methods to solve this kind of exercises. One with difference equation and another method with differential equations. So if you could please upload both methods and also graphical representation.
Okay, I will try to. Okay.
Okay, thank you so much. Thank you.
Okay, you're welcome. Okay, so you have to wait a little to have the slides, but let me know if in many days you don't receive anything. Okay, so I wish you to have time to relax yourself and to learn something from the exercise we made, and we will see us in the new year. Okay, so goodbye to everyone. Thank you for watching, and if you have some other questions, please send me emails, and I will try to answer. Okay, so
Thank you.
bye to
Merry Christmas.
everyone. Merry Christmas to you too. Thank you. Bye bye.